All right, get ready for a showdown. But this isn't about athletes. Nope. Today, we've got two AI models going head-to-head in a battle to see which one can predict a power plant's future. So here's the million-dollar question, or maybe the multi-megawatt question. How much power is this plant going to generate tomorrow? I mean, for the people running the grid, getting this right is absolutely crucial. For us, well, it's the ultimate test for our two AI competitors.
Okay, so the challenge is pretty straightforward. We need to predict the exact energy output of a power plant. But, and this is a big but, our models only get 4 little clues to work with. And all of them are just about the weather.
And what are those 4 clues? Well, you're looking at them right here. We've got temperature, ambient pressure, relative humidity, and something called exhaust vacuum from the turbine. And that's it. Seriously, just those 4 numbers. From that, our models have to figure out a massive, complex operation. No pressure, right?
All right, let's meet our two contenders. It's a real classic versus challenger matchup. Think old school versus new school.
Now, these two models could not be more different in how they think. Our classic, linear regression, is the veteran. It's simple, it's straightforward, it basically draws a straight line through the data. Then you have the challenger, the decision tree. This one's a bit more clever. It creates this big branching flowchart of if this, then that, questions to uncover all the tricky hidden pattern.
You can't have a competition without rules, right? We need a fair way to pick a winner. We can't just eyeball it and say, that one looks better. We need a proper scoring system.
So, how are we going to keep score? We're going to use something called an error score. Don't worry about the fancy acronyms on the screen. All you really need to know is this score tells us, on average, how wrong the model's prediction was measured in megawatts. And here's the key. Just like in golf, the lower the score, the better.
And we're not just doing one simple test. Oh no, we're putting these models through a tough 2-round gauntlet. First up is the initial test, a quick check on some data the models have never ever seen before. But then comes the main event, the 5-fold stress test. This is way tougher. It's a 5-round brawl using all the data to make sure a win isn't just a lucky punch. This is how we find out who the real champion is.
Okay, the tests are done, the numbers are crunched, the scores are in, it's time. Let's see who won.
Okay, here we go, round 1. Look at this. The classic linear regression puts up a score of 3.85. Not bad, pretty respectable. But wait, look at the challenger. The decision tree comes in with a 3.07. Wow, that's a much lower error. The challenger takes a pretty solid lead right out of the gate.
All right, now for the big one, the stress test. How did they hold up? Well, linear regression stays pretty consistent, landing at 3.24. But the decision tree, it just pulls away. Its average error drops all the way down to 2.21. I mean, that's not just a win, that is a dominant performance.
And that settles it. The competition is over. Your winner by a knockout in both rounds is the decision tree.
So just to put that victory into perspective, that 3.7 score on the first test, that means, on average, its predictions were only off by about 3 megawatts. When you think about the scale of a power plant, that is an incredibly impressive level of accuracy.
Okay, so we have a winner. But it's one thing to know who won. The more interesting question is how. What was the secret to its success? To figure that out, we need to peek inside the winner's brain.
Remember, we gave our model 4 different environmental clues to work with. So the big question is, which ones did it actually pay attention to? What did it learn was the most important factor?
And here's the answer. The model basically gave us a report card for our 4 clues. It says temperature was, by far, the #1 most important factor. Right behind it was exhaust vacuum. But here's what's truly amazing about this. This ranking, it perfectly matches what real-world engineers would tell you. So the model didn't just find some random patterns, it actually figured out the physics of how the power plant works. That's incredible.
So, the showdown is over. We've crowned a champion. But really, the work is just getting started. What does this actually mean for the power plant? How can they use this new prediction powerhouse?
Well, this is way more than just a cool science project. A model this accurate is ready for the real world. You can use it for planning out operations tomorrow, for scheduling when to send power where, and just generally making the entire plant run smoother and more efficiently.
But you know how it is, you never stop trying to get better. This isn't the end of the road. For the next match, you could bring in even heavier hitters, more advanced models. You could spend more time fine-tuning the settings, or you could give it even more clues to work with. like what time of day it is or what season we're in. There's always room to improve.
So let's just take a step back and think about what we just saw. We watched an algorithm learn how a massive power plant works just by looking at a few weather readings, and it got incredibly accurate. If we can do that, it really makes you wonder, doesn't it? What else out there can we predict?